Welcome to the Bike Code. I'm your Shafu, and today's episode is with Miao, who's going to walk us through Superboring, which is a DCA protocol. Miao, thanks for taking the time.
Thank you for your attention.
Yeah, for sure. So why don't you
So,
briefly introduce
mhm.
yourself, introduce Superboring, and yeah, let's jump into it.
Sure. So, I am Miao. Sometimes go by nickname Hellwolf. You can find me from GitHub handle Hellwolf. So, I am co-founder and CTO of Superfluid, and but today we're going to talk about Superboring, which is a DeFi product built on top of Superfluid. Specifically, first feature we launched on this DeFi product called Superboring is DCA, dollar cost average. So super boring. The idea is that the most boring way of investing in crypto, and the DCA is the most boring thing we can think of so far. So today we'll basically walk you through how we actually build it using Superfluid protocol in the code level, and yeah, hopefully that can be interesting to people.
Awesome, awesome. Yeah, I'm a big fan personally of DCAing. So it's boring, but I actually personally think it's the it's the only way to actually invest in this stuff. But yeah, let's hear about it a bit more.
Yeah, sure. Now, let me just give you a couple of quick overview of what we have built, how do you actually try it out, and where are the helpful link I think you should have a look after the video. So first of all, you can find the app at the app.superboring.xyz, and currently we're live on base, but we are launching on Optimism and Arbitrum fairly soon. And to use Superboring, it is very easy. You just visit the website, go to the DCA panel, select one of the token you want to trade with, and just follow the instruction, and you will get it done. Right. So it's really, really boring, but it's really, really effective. Right. So for example, if I go to my portfolio, I have been buying Arrow X, which is Arrow token, on base over time, and you can see how am I doing. In fact, I'm doing quite okay. So my average price is still lower than the current market price, right? After the couple of fluctuations in recent market, but I'm doing well by definition DCA, so doing okay. And so it's quite very easily to get started. Just visit app.superboring.xyz. More so you can visit docs.superboring.xyz. There you can find our docs, and there you can also find our white paper explanation how it works and FAQ. So hopefully that's enough information for you to get started. But more importantly, I'd like to use today's opportunity to walk you through the code and how we achieve the DCA in detail.
Awesome. Yeah,
Okay.
let's do it.
Yeah. So first of all, um, the key mechanism is called Torex,
Oh, Meow,
and
could you maybe zoom in a little
yes,
bit more?
sure, of course. Is that better?
Awesome. Maybe on the left side, just a little bit more.
Yeah.
Perfect. Thank you.
Okay, just a bit of terminology. What is Torex, right? So if you visit our docs again, the Torex is actually a acronym in a very unique way. It's called a TWAP Oracle Exchange, so Torex. So it's a core mechanism and the smart contract engine kind of used to make sure that funds accumulated from one side, which is in token, and you swapped for the out tokens in the most dollar cost averaging way. So we use TWAP oracles, specifically Uniswap provides TWAP oracle, right? So time weighted average price, and that's kind of the core engine that's called a Torex mechanism. And more detail you can find from our white paper. You can visit the docs again, and on the bottom of the page of what is Torex, you'll find the white paper. So I'll not open it live here, but I'll just go to the Solidity code straight, right? So uh, the first layer, it is called Torex core. Um, First of all, let me know if I'm too fast. Just interrupt me anytime, Shuffle. Okay, so so this is an abstract contract that basically contains the core logic of the Torex. As you can see, it's a fairly short contract, so we'll dissect it slowly. Um, and the key function are two functions. One is inflow changed. So for people who don't know much about superfluid yet, let me just go through some of the quick introduction about the superfluid, which is superfluid is about, really about how to get paid every second. Also, once you get paid by the second, every second, you also want to get invested every second, right? So this is actually a connected products to what superfluid can do. So the key to implement that logic is to handle the flow action. So let's say if you send a stream of money to the Torex contract, you trigger a hook, a callback, all right, called on inflow changed. So it involves information such as who is the sender of the flow, what is the previous flow rate, what is the new flow rate. So that's the hook, that's the callback. So each time that the flow is changed, it will trigger the logic here. So that's what the Superfluid as a framework would eventually offer for you. And that's how you build application on Superfluid, right? So that's how you get paid every second, then you can get invested every second, right? So this function is fairly short if you look at, I mean, mostly are comments, right? So let's go right in, right? So first of all, there's something called back adjustment. We'll read into it, or what is it about? So in order to know your contribution to the trade over time, we would, okay, so let me walk back. First of all, the trade on Superboring happens from time to time. It's not actually, it's not like every second there's a trade. No, it's actually people pulling the trade into the contract. Think of as, let's say you have 1,000 people sending money to the Torex contract, right? So the 1,000 people will accumulate their in tokens. Let's say in this case, US dollar, USDC, right? So 1,000 people stream the USDC to the contract, then the USDC is accumulated, right? At some point, it makes sense for someone to come in and swap all those USDC according to a benchmark price. We would see what is a benchmark price in a moment. But according to a benchmark price, you can say it's the average price of that moment, and send the result of the swap to everyone afterwards, right? So that's how it works. So it's actually trading happens over time. Let's say intuitively, maybe every 15 minutes, every 30 minutes. It really depends how many people involved in that trade, right? That's how it works. But the problem is that you may join the trade right before the next swap event. We call it liquidity move events, LME, but let's just using the full words instead of acronym. Liquidity movement events, which happens maybe every half hour, maybe every 10 minutes, depends on the traffic. But if you just join the trade right before the liquidity movement event, you should get less from the next swap, right? Intuitively, you should get less. That's not ideal for the calculation. So the way we solve it is that, let's say next liquidity movement is going to happen in 10 minutes. There's people joined before you, like 20 minutes before, right? So in order to make next liquidity movement event equal for you and the person joined before you, so we force you to pay a portion of that as if you joined the trade the same as the previous person. So you actually pay 20 minutes extra trade swap, so that now both you and the previous person have already contributed 30 minutes of liquidity, right? Then in the next liquidity movement event, then you can get proportionally equal amount of our token swapped. So that's how we solve this problem that how can we solve the problem that, okay, you joined earlier or later than the others, and how can you get to the fair amount of swaps? Right? So the way we do that is make sure that we do the adjustment. So even if you joined later, you will pay the back adjustment. It's a really small amount, right? Let's say intuition is at 30 minutes of liquidity. It means that if you join a month, you're trading $1,000 a month in USDC. Every day you are trading how much? $33, right? So the back adjustment would be around $1 or $2. It's a really small amount, but it solves the technical problem. So that's the purpose of this back adjustment function. It calculates according to the flow rate, what are the back adjustment, right? So the back adjustment is based on the previous liquidity movement events and that time gap. So that's the calculation. I'm not going into that function yet. Let's just say see what's next in terms of the function. What's next is now this is a superfluid part. So we have to give sender something called units. Again, I have to introduce superfluid, I guess, inevitably. So the way that superfluid distribute money to people is using something called a distribution pool. Think of a pool is a way to distribute money proportionally according to how many units you have, right? So the way that in Torex, how it works is that the higher the flow rate, the more units you have, right? So intuitively, I mean, if you send more in tokens, of course you have to get more exchange proportional to your flow rate, right? So that's so-called a distribution units. So that's kind of it. That's two problems to solve. One is how to do back adjustment. The other is how to assign proportionally the units in order to send back to the sender. So that's kind of flow rate, the flow hook handling. On the high level, it's just two blocks of code. One is do the back adjustment. The other is update the distribution units. That's it. Happy to clarify so far any problem that any kind of thing that are not clear. So far so good. Or?
Yeah, I'm not 100% sure I understand the back refund. Yeah.
Okay, so let's. So let me try to draw. So let me see if I can explain using the other view of it. Okay, so I have a diagram here, hopefully that visualizes things a little bit. So again, look at this water analogy, right? So it's like a water tank. It accumulates liquidity. The blue liquidity is in token, let's say this case USDC. So you have many others, right? Any number of people can do money streaming to the water tank over time, right? So the water is going up, liquidity level is going up over time, right? But then what happens is that someone, let's say this another entity called a liquidity mover, needs to come and take all the water, exchange the USDC to ETH, and send back to everyone, right? That has to happen from time to time. That's what this Torex contract trying to solve for you. And the way to make the price fair is that we check the price from the Uniswap TWAP oracle. We'll see in a moment how that price is calculated, but ultimately each Uniswap pool provides an oracle, and it's called TWAP oracle. There you can get the objective price according to the past history of exchanges, and very closely tracking the average prices, of course, for that pair of the market price. So there's observer smart contract, which is taken as a objective observing data points. So the liquidity mover just need to satisfy that observation, which I will show in the next function, right? It will explain that. But the whole point is that this exchange will happen from time to time, and the result of the swap is sent back to everyone as a distribution in chunks.
Okay.
The thing about the back adjustment is that because let's say Alice joined earlier, so accumulated most of the water is from Alice, but Bob joined almost like last minute, then intuitively Bob should get less out tokens because Bob only contributed a little bit, right? That's kind of difficult to handle. The way we solve it is that we say if Bob joins later, he has to pay up backwards in a way, adjust as if he joined at the same time as Alice. So that's so-called a back adjustment. So that even if Bob joined later, he has to pay up the same amount of time as if he joined the same time as Alice joined. Does that make sense?
Mm.
So this way, accounting-wise, it would be easier so that Bob and Alice would have the same amount of contributions proportional to their flow rate, of course. So that no matter how late you join in the process, you always pay up according to the time checkpoint, same for everyone, right? So you always pay up until that point. So your flow rate will multiply by the time gap, even if you join later, so that then it's easier for the accounting calculation that everyone has pay up, that amount. So that's a back adjustment process. So remove that differences in terms of when people joined. That's kind of the technique here.
Okay.
Okay.
Yeah.
Okay, so basically these two steps basically explain that one is about back adjustment, the other is assigning distribution units to everyone according to their flow rate. That's done. So that's how we handle the accounting in terms of your contributions. Now, the step 2 has to do the liquidity movement, right? So somehow liquidity mover needs to swap all this liquidity for something else and send to everyone back, in a secure and objective way. So let's look into this function. So there are a couple of steps. First of all, we get to the liquidity estimations, which okay, so let's look into this function, because this function gets something called a get benchmark quote. This is where we query the Uniswap price, right? And the implementation is separated. Oh, by the way, maybe I should share where the code is, because if I go too fast, because I only have 1 hour, right? So if I go too fast, people can always refer to the code later. Let me just send a link. Hopefully that's going to be helpful. Is there any way I send a chat message to this software? I should send you to Telegram instead.
Yeah, Telegram would be best.
Okay. So this is the code. You can find it later. And so in the get liquidity estimations, we will look into an implementation called the Uniswap pool TWAP observer, which is wrong. So let's the code. But let's look at the interface first, because the implementation might be daunting. The interface is easy. You have a few functions. One is create a checkpoint, and you also can see the duration since last time you created the checkpoint, and then you get the TWAP since last checkpoint, right? TWAP means time weighted average price. So this is literally means the TWAP since last checkpoint, which is the time. So what's the average price since last checkpoint and now? That's literally what it achieves. There are different implementations. In this particular case, we use Uniswap pool, right? So Uniswap allows you to query that TWAP information, and in the code I put enough references so you can always walk back and understand how everything works from all the references. I hope the comments helpful. So the way that you implement this is use Oracle library from the Uniswap v3 peripheral contract, and they provide a couple of utility for you to re-implement this. So we actually have to re-implement the checkpoint model so that it best serves the purpose. But I don't think I have enough time to go deep into how every part of Uniswap works. I think they have quite good references and documents, so I listed enough in the notes. So if you are interested and you're not familiar yet with it, you can always look into the references. But I just give you a feel is that in order to get the TWAP since last checkpoint, in Uniswap, you would have to get something called a tick cumulative value. And you have to remember what's the last tick cumulative value. You do a delta of that and you divide by duration, then you get a tick. The tick number itself is not price yet. You have to give the Oracle library from the v3 peripheral from Uniswap, give the tick and give the amount, then you can get the out amount. So basically you get a price based on the amount of input and you can get the amount of output. That's basically the price. You use the Oracle library to do that. In order to get the tick cumulative, you have to use the Uniswap pool interface called .observe, and you provide, according to the interface, how many seconds ago you are talking about here, right? So that's basically the how you call the function, right? So then with this you get a tick cumulative. That's it, right? So the reason why we have an interface as opposed to just a straight Uniswap implementation inside Torex is because we anticipate that you might have a different TWAP provider. That's one case. The other case that actually we are already facing is that you might using two different Uniswap pool to get a price or better price reference. What do I mean? For example, if you want to get a what is the meme coin we can talk about here, DGen token base, let's say. In order to get a US dollar price of DGen token, the better way using the Uniswap on base currently is actually through USDC to ETH and ETH to DGen, because two pairs have a bit more liquidity. So in order to achieve that, you can use two Uniswap pool and just concatenate them, connect them, and you get a price from USDC to DGen. So that's no longer a single Uniswap pool implementation, but the interface can be the same. So you are using the same interface, but with a different underlying implementation, right? And the Torex don't really care how you implemented it. So that's we abstract that information away so that you are free to implement whatever TWAP observer as long as you follow the correct spec and the interface, right? Then you can have a correct implementation that the TWAP can use. Sorry, Torex can use. All right. So back to the Torex. So when we do a liquidity estimation, it's basically getting the benchmark quote. Get benchmark quote is implemented using the observer, right? So we say get TWAP since last checkpoint, and then you get the price, right? So this is a part of the interface of ITWAP observer. That's how you get the benchmark price, right? This slide. Okay, so let me roll back the stack. So we're back to the move liquidity step. So just a reminder, where are we? In the step 2, we have to move the liquidity. So we'll move to the blue liquidity to, I don't have a color for the auto token, but let's say red liquidity. Okay, so from the USDC to ETH. Let's make an example. So the first step is getting the price. Now we get the price. We know what are the in amount, meaning that the amount of blue liquidity, and we also get the minimum out amount we should get from the liquidity mover. So that's a benchmark price. If you cannot satisfy that, then you can't make this transaction pass, right? Let's ignore this line for now. I will go back to that. But step one is transfer in amount of in token liquidity to the liquidity mover. What does it mean? Right. So this is a normal ERC20 transfer. We say, okay, in token you transfer to the message sender. The message sender is the liquidity mover. It's a contract. You give it back to that amount of in token. It's like you are lending the token to the liquidity mover, and let the liquidity mover find the out token liquidity. However you find it, it doesn't matter. You can find it from Uniswap, you can find it from your own pool. It doesn't matter to the Torex contract as long as you can satisfy the benchmark price, right? But in order to do that, we first lend the tokens to the message sender. Then we call the callback of the message sender. So message sender has to have this interface. And we call the callback, say, hey, liquidity mover, since you asked, now I lend you this amount of in token. Now please give minimum amount of out token to me, right? And I pass along some of the data which you passed to me, right? This is kind of one technique so that you have a context for the liquidity mover contract. And we also tell you what is in token, what is out token. If you can if you can pass this callback without reverting, we will then check the outcome of it. The outcome is that we will check our balance of this contract, right? If the out amount from this measure is less than the minimum out amount, then as a liquidity mover, failed the job. Then we revert the entire transaction. So the lending never happened, as if it's atomic, right? So we lend you the amount, find it in the same transaction. If you find it, we complete the transaction. Well, we go forward with the transaction, right? So far so good.
Yeah.
Yeah. So the step three basically go to the observer and follow the contract. Say, okay, now we create a new checkpoint because everything so far is good. Create a checkpoint. So the observer reset the time window of average price from the new point, the liquidity moving point, to the future, right? So this is where the time checkpoint is created. The number 4, all right, remember the here diagram, you have to send all the out tokens to everyone, right? So basically say out token distribute to pool. We send everything, we distribute all the out tokens to everyone, right? Distribute to pool, right? The pool is the units is set up in the previous callback, which I was trying to explain. So that's all, 4 steps, right? Let me summarize. So lend token to the message sender who is a liquidity mover. Call the callback of the liquidity mover, telling that what is the number of in token you are gonna get, and what is the minimum out amount you should give it back in terms of out tokens. And if you satisfy that benchmark, then we don't revert. Otherwise, we revert. If everything is so good so far, we create a new checkpoint in the observer, and in the end, we distribute everything to the traders. So that's the entire core logic in a high level overview of Torex core.
Okay.
Right.
Okay.
Yeah. So yeah, I think it's kind of showing that how the programmable money can enable this kind of new way of doing that kind of trading, right? So I think that's kind of the demonstration of that. But at the same time, this is only an abstract contract, so it probably begs the question, what's the actual deployed contract look like, right? So we can go to
Yeah.
that. Next, right? So summarize it that Torex core and TWAP observer is the core of the core logic, basically. And one of the implementation of TWAP observer is a Uniswap V3 pool TWAP observer, which is single pool implementation. And we also have a multi-pool implementation coming up, which allows you create a observer that connects to Uniswap pool who has sort of a shared intermediary currency, most likely ETH. So for example, USDC to ETH and ETH to DGen, for example. Right. Okay. Is anything worth mentioning more? I definitely skip some of the too much of detail, otherwise we'll run out of time. Hopefully that's okay.
Yeah.
Yeah. I believe it will be also on YouTube, right? So if there's any people ask any question, I can monitor and just answer there also, whichever platform is suitable. So let me move forward. We have 10 minutes. How much time I should leave out for the end? I have 1 hour in total.
Yeah, it's 1 hour, like 30 minutes from now.
Okay, cool. So let me just go to the Torex, which is no longer a. Let me just split the screen. So in the bottom, it's the Torex 4, right, which is an abstract contract, which requires implementation of available in tokens. So that's virtual. What else is virtual? That's only one, actually. It looks like. All right. So why we have created another sort of wrapper over it, right? Why is because first of all, who is providing the callback? The own inflow changed. So in the core logic, it doesn't assume it's a super fluid, right? So just make sure that the core logic, the Torex core is more abstract and more kind of reusable. We just have the core logic. So the actual one that's providing the callback of inflow change is the super app. Again, it's a super fluid concept. You may visit the docs.superfluid.finance, which means where it should have a explanation what is a super app. In short, super app is a way for you to create a super fluid application that handles callbacks such as flow rate changes as a contract, right? So that's in short. So Torex is a Torex core, right? So it basically implements whatever missing implementation in this core contract, and also provides where the hook is actually called, right? And there's a bit more, right? So let me read the notes here. So in addition to the Torex core logic, it uses Super App Framework, which supports the cash flow automation. And furthermore, it also allows fees, right? So in the core logic, there's no fee involved. But what if we want to implement a fee on top of that? So this is an opportunity for you to actually inject the percentage of fees, but not as part of the core logic here, but as just something built on top of it. We'll go there in a moment. But also note that this is not upgradable contract. So this is one of the design choices we made. We want to make sure that people trust this contract to extent that we cannot rug pull them.
Yeah.
Right. So this is super important design choice, but with a caveat, because it does allow something called a controller who can decide what is a fee amount. Right. So controller actually can decide what is the fee and where the fee goes. Isn't that contrary to the upgradability, immutable aspect, right? So you may ask already. So the way that we make that work together is that the controller can decide what is the fee max, but we constrain that there's a maximum allowed fee. So controller can throw a random number or can
Yeah.
be hacked. But we say as an immutable contract, we can only tolerate up to certain amount. So in a production deployment that we have, the number is actually set to 3%. So
Mm.
it's not great if that happens, but at the same time we can block the controller from taking everything, right? So when that actually happens, of course you have time to unwind or somehow fix the controller. But at least from this contract perspective, we simply block that possibilities. If a controller wants to take a fee more than 3%, it's gonna be reported as an internal bug, recorded on chain. So runtime verification can actually see that something's wrong, and then we have a further step we can take. So that's kind of the design choice. So immutable with variability, but with sort of um, how do you call this? Short circuit mechanism in a way,
Yeah.
right? Okay. Maybe let me just go to some of the interesting implementation aspect, because maybe we don't have time to go through entire contract. It'd be too detailed to explain all the superfluid aspect, but one of the things I think is interesting to mention is that the way we interact with controller in the Torex is through callback again, right? But what if the controller blocks the callback by consuming all the gases? Wouldn't that be bad, right? So this, I hope it's interesting that for people to know that when they have the same conundrum, the way you can solve it is that you give controller callback a, a gas limit,
Yeah.
right? And if the controller used all the gas limit, then its internal bug will flag it. So we actually emit a controller error so that we we don't fail the Torex trading. We only say there's a controller error, so it's on chain. You can see an event. So if you see the emit controller error function, it will emit a controller error. We'll log the reason and we'll increase the counter of the error. This usually shouldn't happen, right? And if it does happen, we'll debug the controller. Controllers can be upgradable. In let me in detail, the controller, one of the controller implementations called a, well, you guess it, Superboring is actually a Torex controller. So that's actually the controller who decide what are the fees, where the fee goes, and putting extra logic on top of otherwise a simple Torex. So, but the controller is upgradable. The Superboring is upgradable, but the Torex is not. So controller have callback to handle extra, logics, but those callback, we don't assume they can never go wrong. If they go wrong, in whichever way, we will record it as part of the Torex internal error, and we will have on-chain visibility, and we can do something about it. That's kind of a design choice, right? So one of the thing to make sure that actually happens is that we make sure there is a gas limit for the controller callbacks. And here has a very interesting, I hope it's interesting that the technique that you need to distinguish between the genuine gas limit error versus the user didn't provide enough for gas limit to the entire transaction. So these are different use case, different nuanced scenario. And Superfluid actually provide a utility function that address the differences. There's enough comments in the Superfluid code, and I'm gonna send a link so that if you're curious, you can read into the that. Let me maybe share the screen also. That. So there's an entire comments about a very little amount of code to explain why there's a difference between if the entire transaction doesn't have enough gas versus if the callback consumed all the gas. There are two very distinct cases, which I think if you need this level of distinctions in a particular use case, this is what Superfluid codebase has a solution, and there's enough comments you can read into it. And happy to be connected and answer more detailed question another time. Okay, so there's a controller hook, and the other aspect, as I said, is fee short circuit. So let me read that part of code also. So there's a line say protect traders from rogue controllers, right? So we basically say, okay, if you want to charge us a fee that is more than what we can tolerate, immutable, is 3% in the current configuration, and you cannot change it, right? So the Torex say we can tolerate up to 3% of fees. If you charge more than that, we're assuming something wrong with you, with the controller, I mean. And then we say we set the fee to 0. So we assume you are going something crazy, and we said don't give you any fees, right? So this is a short circuit code, right? Yeah, I think we're approaching the end. Instead of going too much of a detail for the rest of the code base of Torex, let me just probably zoom out, just say that as a sort of a high-level overview that we have the Torex core, which is the core logic of Torex itself, which involves two steps. One is accumulating liquidity for traders and move liquidity from time to time, right? So that's a core logic encoded here, and it requires benchmark price, which can be implemented using the Uniswap TWAP Oracle, and the interface is called TWAP Observer, and there's implementation using single pool, a single Uniswap pool for the TWAP Observer. And the next is a Torex, is a concrete implementation of the Torex core using Superfluid and allowing a concept called controller. Let me go to the controller interface, which I didn't show. So controller basically additionally allows a callback called an inflow change and liquidity moved. So you can inject additional logic. But in order to protect Torex from bad implementation of the controller or hacked implementation, it has self-defense mechanism, right? So namely, allow a maximum fee short circuit. The other is a specific technique, prevent callback from blocking the entire transaction forever using a gas limit. Right. That's kind of the overall summary. And one of the implementation of controller that is in production is called Superboring. I feel that we might be benefit from a future follow up if people are interested, because I think there's a lot to talk about Superboring still, but I think it's already a lot of concept already. I talked about the Torex itself, right? So maybe what I can show more without going into the Superboring is how we test the Torex, right? Maybe that's interesting, just to focus on just Torex.
Yeah, for sure.
Yeah. So in terms of development framework, which I didn't mention, well, we use Foundry, not surprisingly probably, and we're quite aggressive tracking the latest compiler, but we are stuck with Paris EVM version because we support the Celo network also, and they don't support all the latest features, so that's unfortunate. So until the upgrade, we have to go with it for now. That's probably the only network that I know of that's still stuck with the older EVM feature set. And we extensively use the uh, fuzzing test. So most of the tests are parameterized. So uh, and can be a bit of learning curve for people even want to start a test, but it should be intuitive. So for example, let's read into one of the test case, right? So there's a test library called framework called a test common, right? So there we add common verbs for testing, right? So test a change flow, advance the time, move the liquidity, advance time. Superboring has staking, so we also have helper function for updating stake. So test cases all explained in a kind of way that you can read easily, right? So all the nitty-gritty detail are abstracted into a function, right? So you basically create a test case that's as readable as possible. But with the power of fuzzing, of course, you want to actually parameterize as much as possible so that you don't hard code any number in order to increase your code coverages, right? So here, most of the most of the, I think in this particular case, all of the parameter are all of the variable is parameterized, right? So basically, function will spit out a bunch of random mutations of different values, and that's it, right? And so this is nothing too strange. Maybe the only thing that worth mentioning is how some of the test cases are encoded. So then the name is, so one of the dilemma probably some people may think it's controversial, but some may appreciate the way it is. How do you name your test cases, right? So one of the dilemma is that in the very beginning, we had some test case named very verbosely, test this scenario with a long English word. But after a while, you run out of way how to express it. Either the function name become too long, or either become very unintelligible for most people. So one of the technique that I think in this particular case is useful is just you come up with your own kind of coded language, which of course better have comments, right? Otherwise people will be confused. So it is indeed a commentator, I believe. If not online, I think it is somewhere else. It's in the unbridled, probably. All right, so there's a encoding language, right? So F and C means flow. M means which tester, right? So if you have involved two tester, you can say this is an action of F, one letter, and involve which tester. So you have 0, 1, 2, 3 named testers. And what is the other actions? Basically, you have a small encoded language so that you free yourself from, thinking about how to name some more mechanical test cases in a very, so it's kind of, it reads immediately, okay, you want to do a flow for Alice. 0 is Alice, and there's a movement of time. Time movement is delta time is also a parameter, so you can move 0 seconds or any seconds, right? So there's a T. L is liquidity moving. There's another T, which is moving time. C means close the flow, and Z means end, right? So this way you don't have a English wording problem. You just simply encode the test name with your own little language. So we did use that in this case. So I just find it's probably worth mentioning, but you don't have to take this as advice. Just one thing that I find it's probably useful in some cases. And last bit I mentioned is a sort of conclusion, I guess, is a specific technique that I think might be interesting to some people. I understand that the Foundry already have invariance testing, right? So it's something you can create a long sequence of event actions and see if the invariance still meet. That's one technique that we could use. In Superfluid, we use a similar, which is more original, prior developed tooling called Echidna, which does a similar thing, but with a bit more nitty-gritty implemented internally. But in terms of Torex, I actually used a bespoke mechanism that I don't think it's commonly used, but it sits something in between of the invariance test in Foundry and fuzzing test. So I kind of abuse the Foundry's fuzzing to create random sequence of events. So this way I can run local testing without using invariance test. So just say that this might be interesting for some people to copy, but maybe you just use a Foundry invariance test straight away. It's fine also. So just to give you a feel how it works. So how it works is you create a Foundry test, but you provide something specific. You say, I want to randomly 10 actions, right? 10 random actions, and action is a struct. So this way, you're actually testing 10 random actions in Foundry using just the fuzzing itself, right? And the action is just a struct. You say, oh, I want to define what's the action type, right? So enum. Who are we talking about here? What's the time delta for this action? What's the value for the action, right? It's like, depends on the action, some different applications. So Foundry can actually fuzz a array, a fixed size array, actually, fixed length array. So it's an interesting hack. I would say that if you want something in between the Foundry invariance test and something that can test the random actions, because this can greatly increase your coverage without having to think all the cases, right? You can run with like 10,000 iterations with Foundry, right? Foundry has a forge test. Was that wrong or no? I don't remember. Fuzz runs, yeah. You can say 10,000. You can run this on a beefy machine. So what I did, for example, is I run in parallel 10 Foundry tests in a beefy machine so that I can actually have increased coverage without thinking through everything in the very beginning. But with this can discover new cases. And what you should do is encode those new test cases into a separate test so that you can have a regression test later on, right? But this can discover new cases, hopefully, for you. Right? So this way you don't have to think, oh, I'm too lazy to write all the test cases. Let me just fuzz it and to see which test case I fail. Right? It requires a little bit of work. Say you say what type is it, and then you have a big for loop going through all the actions, and for each action type you do a particular handling. Then you have a poor man's stateful fuzzing, I would call it. Right? So it's not difficult to set up, and it helps for people who want to be lazy in the beginning, because people don't like to write tests, right? I can tell a lot about writing tests, but people generally don't write, and this is one way to get be lazy, but without being kind of regretful later, right? You don't want to regret that you didn't test anything, but you don't want. But if you want to be lazy in the beginning, so this could be one way to discover those cases, right? So. Okay, I think I used all the time for today. Do you think I should mention anything more?
Yeah, I think we should do a follow-up now. There's still so much in this.
Um, mhm.
Yeah.
For sure. Actually, the Superboring has a whole slew of boring programs, right? So we just touched. So we built the Torex core, we built a Torex, then we built a Superboring on top of it. And we have a bunch of programs such as referral, code, distribution fee, emissions, all those interesting stuff. So it's in itself a separate core, I would say, if people are interested. And I hope I can share more technique that I will use in this project at some point. Yeah.
Definitely. Really interesting. When was Superboring launched?
We actually just launched just a bit over a month ago,
Oh, okay. Congrats.
officially, publicly. Yeah, thanks.
Nice.
Yeah,
Nice. Nice.
yeah, we're launching more networks and um to Arbitrum and to Optimism soon. And yeah, there's a lot of new trading pairs you can try on Arbitrum, especially Arbitrum. Um, there's a lot of activity there, DeFi activity there. And on Optimism, it's something special for us because we uh, powered the Optimism's RPGF4, right? So recipients are using Superfluid to receive their OP grants, and we offer them a platform that they can dollar cost average buying ETH with their OP, or eventually maybe they want to sell some of the OP uh, for dollars, right? So all those are going to be possible with a Superboring. So they receive it in streams, then they buy with a stream, right? So that's our thesis: get paid by the second and get invested by the second and get richer by the second. So that's kind of our our goal, our vision of the world.
Nice, nice. That's a good pitch. That's a good pitch.
Yeah,
Awesome, Miao. This was super interesting, man. Yeah, thanks for doing this.
yeah.
Um,
Thanks.
I'm gonna put the GitHub in the description down below, the super boring docs, the super fluid docs. Anything else?
Yeah. Give us some feedback on Farcaster and Twitter. Give it a try. Post anything on our GitHub, maybe an issue or something. Ask questions. Whatever channel you think you feel comfortable with. Really would like more people to know about Superfluid, know about Superboring, and yeah, and let's get connected.
Awesome, yeah. Then yeah, thanks again for doing this. This was super fun.
Thank
Thanks
you.
guys for tuning in, and I will see you in the next one. Bye bye.
Bye bye.